They're given the D is a metric which are given. K into D is also metric. Is also metric. The same set text provided is positive. Provided K is positive. Right? The same condition which was checked, which is of course already satisfied. So hence it is a metric on the same set X. Infinite would write a answer, but exact అయితే countable. Infinite would write a. Understand? Infinite would 100% right. But exact answer అయితే uncountable. ఇది కూడా one of the option right. Infinite would అది పెట్టచ్చు కదా problem. So next is interior point. Start with the metric space again. And you start with the set which is subset of X. A point that you started with which is in E is said to be interior point. Of E, if there exists a neighborhood, at least one neighborhood, means where that neighborhood center at P with radius R is contained in E. This is what actually, this is my metric space. This is what actually a subset of X. In order to check a point which is interior point of E, that point should be a point of E. Right? If you take a point of E, when you say that it's an interior point, you need to provide some neighborhood which is contained in E. Right? Q, suppose you take a point of Q. So can you provide a neighborhood which is inside? This is my neighborhood around Q, which is inside E. Therefore, it's an interior point. It's a point of E. Is it interior point? No, because I never provide a neighborhood which is inside. This region, shaded region, is outside of the set. Is outside of the set. Hence, it's not an interior point. Means interior point means what? You need to provide at least one neighborhood around that point, which is contained inside the set. Example, suppose you start with R with respect to standard metric. You start with any set. Suppose a simple open 0, closed 1. This is my real line. This is my set which are working. Right? So is it an interior point? No, because it's not a point of the set. This is outside of the set, right? This is my set. In fact, this is my set. This is my set. So this is outside of the set. Therefore, point is not a point of E. Hence, it is not an interior point. Is it an interior point? A point which is bigger than or equals to 1. In fact, bigger than. In fact, bigger one. Is it interior point? No, because it's outside of the set. Okay. Is it interior point? Yes. Because what is the neighborhood yesterday I told you? When you are working with the usual metric space, that neighborhood is nothing but bounded interval, open bounded interval. P minus R to P plus R. Yesterday we have discussed. Right? So therefore, I can adjust very small neighborhood, teeny neighborhood, which is inside the set. In fact, you can take R is equals to minimum of this P minus 0 and 1 minus P, which works. Right? So this is my neighborhood, this neighborhood, P minus R, P plus R, which is inside the set. This is inside the set. So therefore, P is an interior point of the set. Is it an interior point? Yes, I can adjust a neighborhood which is inside the set. Is it an interior point? Yes, I can adjust a neighborhood which is inside the set. Is 0 is an interior point? No, because 0 is not a point of E. 0 is not interior point. Question is 1 is an interior point? The answer, no. Why? Because this green region outside, right? The portion which is right side to 1, the portion which is right side to 1, which is outside of the interval given set. The portion which is right side to 1, which is outside of the set. Hence, 1 is not interior point, right? So what are the interior points? What are the interior points? 0, excluded 1. All the points inside 0, 1. The set of all interior points, which is denoted by int of e, are equals 0. This is Siemens notation. This is routine notation. You can follow any notation according to your exam, right? The set of all points, this is nothing but what? Interior of the set. Set E that is denoted by int of E or E power naught, E prime naught, right? So therefore, this is nothing but int of E, right? Suppose if you take the same example, x with respect to discrete, the same which is set, which I consider 0 close to 1. Is it open? Is it in, what are the points are interior points of E? So the again idea is same. It's open 0 close to 1. Is it interior point? No, because the point which is outside of the set, therefore it's not interior point. Is it interior point? No, the point which is outside of 1, therefore it's not interior point. So question is it interior point? Yes. Why? Because I can adjust a neighborhood. Yesterday I told you the neighborhood of P, in fact, in a discrete metric space, the neighborhood of P with radius 1 is equals to full X whenever R is bigger than 1, or singletons, which are R less than or greater than equals to 1, is less than 1. It greater than or equals to 1 means you can take only this. Greater than 1, this is less than or equals to, right? So if I choose the radius, now I'm working with P, I'm going to check whether P is the interior point of the set or not. Now what I do is that I can choose a very teeny radius 1 by 2. You know, this is less than 1, therefore neighborhood of P with radius R is nothing but what? Singleton P. You know, singleton P is nothing but what? Singleton, you know, P is an element of E. We have taken element which is in E. Therefore, singleton P is always subset of E. Therefore, I found a neighborhood which is inside E. Therefore, P is an interior point. P is a interior point, right? So this is an interior point because the same neighborhood which works. This is an interior point because singletons. This is a neighborhood which is inside the set. Is one is an interior point of the set? Yes. The same strategy. If you take P equals to 1, which works, the same neighborhood. So P also interior point. This is also interior point. This is also interior point because neighborhoods are singletons. I can adjust the neighborhood as singleton, whatever point you chosen. Along with that point, I can choose the radius is very less than 1. That with that neighborhood which is inside the set. Therefore, every point of the set is an interior point. So what is interior of the set? Set itself. Right? So this is interior of the set. Suppose.
Sir, what about border element 1?
Which one? One?
Border
This one?
element 1. 1, 1, sir. 1.
Yeah, that's what I'm telling. If P equals 1 also, this is true. This is P is any arbitrary element in E. Understand? In particular, P equals to 1 also true. P is any arbitrary element of E that was chosen, right? Any element that have arbitrary element which is in E. Therefore, which works the same center, same radius, in fact.
Okay, sir.
Right? Now we can take this idea R with respect to Euclidean metric or usual metric. Suppose same set which I am taking. You know, it is clearly subset of R, no doubt. This is, I'm going, see, we are working with a plane. So therefore, this is my 0, this is my closed one. Right? Question is it an interior point of the set? First, is it an interior point of the set? No, it's not a point of this. Is it interior point? No. Is it interior point? No. Is it interior point? No, because they are not points of the set here. Question is it an interior point? No, because yesterday we have seen that neighborhoods are a neighborhood of a point with center R is nothing but open circle center at P with radius R. Interior of the circle, center at P with radius R. So I never adjust a neighborhood around this point. This is my P. So what is my neighborhood here? This is my neighborhood. Center at P with radius R. You know, this region is outside of the interval. This region, of course, this region is outside of the interval. Therefore, that point which is not in the neighborhood is not inside the set. Therefore, that point is not an interior point of the set. Right? Any point that you started with, it's not an interior point of the set. Right? Any point that you started with is not interior point of the set with respect to this metric space. Right? So therefore, this is about the interior point. Next, open set. So again, you started with the metric space. Again, you take a subset of X is open if and only every point of E is an interior point. Right? So let me give an example. Right? Start with R with respect to visual metric. Right? So is it open? Yes, 100% open. Why? Because is it an interior point? What is the definition? Every point of E must be interior point. It took any point of E that must be interior point. I don't bother about the points which are outside of the set. In fact, what is the definition? Every point that you have chosen in E, that you have taken in E, that must be an interior point. So suppose I'm going to take this P. Is it an interior point? Yes, we have seen just now. I can find neighborhood which is inside the set. Is it an interior point? Yes, I can find some neighborhood which is inside the set. Hence, you know, this point also interior, this point also interior. So every point is interior, hence it is open. One in R. Right? Suppose if I take the same example, is it open? So you take this. So this point is interior, this point interior, we have seen, this point is interior, we have seen. But what about this point? This point is not interior of the set because this portion is outside. The portion which is right side to 1, which is outside, therefore 1 is not interior point. Hence, it's not open. At least one point is not interior means it's not open. Right? But if you take this idea in this different metric space, where discrete, suppose you start with any subset of X. Question is it open? Yes, because you give me any point of E, you give me any point of E. This is my subset of E, suppose you take. This is my point of E. So I can adjust some neighborhood. What is my neighborhood in fact? Singletons, points. Neighborhood of P with radius 1/2. You know, this is my singleton P, which is inside this. Therefore, P is an interior point of E. P is an interior point of E. Therefore, this is true for every point of E. That means what? Every point of E is an interior point of E. Hence, it's an open. This is open. What is E actually? E is any arbitrary subset of E. So therefore, what is the notice? Every subset of discrete metric space is open. Right? This is what actually open. Next is limit point. Suppose you start with the metric space and again E is subset of X. You take a point which is not necessarily in E, it is a point of X. A point which is in X, not necessarily in E, need not be in E. It is a point of X, that's it. So a point of X is a limit point of E if and only every neighborhood of P contains at least one point of P other than P itself, other than point itself. In fact, other than P itself. That means you take any neighborhood. This is my metric space. This is my, suppose you take this. This is my city. Right? This is my city. Question is it, suppose you take this point. Is it limit point? Yes. Because you take any neighborhood, it contains at least one point other than the point itself. This E point only. Small, it can take any small teeny neighborhood. It contains at least one point other than the P. Therefore, P is a limit point. Is it a limit point? Is it a limit point? Yes. Give me any neighborhood. It contains at least one point of E. At least one point other than the point itself. Right? Is it a limit point? Is it a limit point? Yes, because you take any neighborhood around P, it contains at least one point. Is it a limit point? Yes, you give me any neighborhood, it contains at least one point other than P itself. Therefore, that is what notion, that is exactly same as saying that any neighborhood of P intersects E other than P itself. That is this. Right? Such a points you take in a set. Such a points you take in a set, that is what actually derived set. P is a limit point. Such a collection that you take in, in a set, that is nothing but what derived set, which is denoted by D of A, and in rooting it is denoted by E prime. D of E, both notions you can follow, is nothing but what derived set. This is a rooting notation. This is what Siemens notation. You can follow any notation. That means what? Or set of all limit points of the set is nothing but what? Derived set of E. Derived set of A. Okay, let me give an example. Suppose you take this. Right? Yeah. You take any member which is a real number. In fact, you take a point which is less than 0. Is it a limit point? No, because I can adjust some neighborhood which never intersects the city other than the point itself. A neighborhood low, set low point level other than P, therefore it cannot be a limit point. Is it a limit point? No, I never adjust, I can, in fact, I can adjust in some neighborhood which never intersects the city other than the point itself. Is it a limit point? No, I can adjust some neighborhood. In fact, I can take a neighborhood, it's p minus 1. R is equals to p minus 1, p minus r, p plus r, in fact, which never contains any point of the city. In fact, any point of the city. Therefore, it cannot be a limit point of the city. Is it a limit point? Yes. You give me any neighborhood which intersects the city other than the point itself. Therefore, P is a limit point. Is it a limit point? Yes. You give me any neighborhood. These left points, look at these points. There are uncountable many points. So, other than one, there are so many points. At least one point are required. Therefore, one also limit point. Is 0 is a limit point? Yes. Because you give me any neighborhood, this point is a point other than 0. You give me any small neighborhood, it contains at least one point other than point this. Right? Therefore, what are the limit points? 0 is a limit point. Between 0 and 1 also limit points. 1 also limit point. Therefore, what is the derived set? This is my derived set. You follow one notion. Right? Suppose you take this. The same example that you started with. Yeah. Is it a limit point? No, because I can adjust neighborhood as singletons. We've seen just now. I can take this neighborhood as singleton, centered P. Does it contain any point of P? No. Therefore, it cannot be limit point of the city. Whenever P less than 0, the points which are outside of 0 means left side to 0, cannot be limit points of the city because I can adjust the neighborhood as singletons, which never contain any point of the city. In fact, when you take the P bigger than, is it a limit point? No, I can adjust the neighborhood as singletons. Right? This neighborhood never contain any point of the city. Therefore, it cannot be limit point. Okay. Is it a limit point? Again, the same neighborhood as singleton. You can take this neighborhood as singleton. Right? This neighborhood doesn't contain any point of the city other than P. Therefore, P cannot be limit point. Is it a limit point? No. Is it a limit point? No. Therefore, what are the limit points? No limit points. In discrete metric space, there are no limit points. Therefore, that means what? You started with any, so every subset of a discrete metric space has no limit points. In a metric space X. Right? This is about what is that? Limit point. Next is closed set. So again, you start with the same metric space. You can start with same metric space. This is my subset of X. So this is closed. It to be closed in X if and only if it contains all its limit points. It contains it's all its limit points. That is E prime is the subset of E. Right? It contains all its limit points. Whenever P is a limit point of E, that P must be inside E. P must be inside E. Whenever P is a limit point of E, P must be inside E. Right? That is what actually closed set. Suppose we take this. R with respect to usual. Is a closed set? Suppose you take this point 0. What is the definition? It contains all limit points. So 0 is a limit point. Yes or no? Why? Because you take any neighborhood, it contains at least one point other than 0. So 0 is a limit point. 0 is a limit point of the set, but 0 does not belongs to E. Therefore, E prime is not subset of E. Therefore, 0 is a limit point, but 0 is not a member of E. Therefore, E does not contain all its limit points. In fact, E does not contain that limit point 0. Therefore, it cannot be closed. It cannot be closed. Suppose you take the same example. Suppose you include 0. Include 0. Is it limit point? No, because I can adjust some neighborhood which never contain any point of the city. Is it a limit point? No, I can adjust a neighborhood which never contain any point of the city. Is it limit point? Yes. You give me any neighborhood, it contains at least one point other than 0, which are in fact right side to 0. So 0 is a limit point. Is it a limit point? Yes. You give me any neighborhood, it contains at least one point other than this. Is it a limit point? Yes. Give me any neighborhood, it contains at least one point other than 1. Therefore, what are the limit points? 0, 1. What are the limit points? 0, 1. Info, this is nothing but what? E. So this is subset of E. Therefore, E contains all its limit points. Hence, it is a closed set. Suppose you take the same set. Is it closed set? So we have seen that E has no limit points just now. In any discrete metric space, E has no limit points. So E prime is empty. Empty set is subset of itself. Therefore, E contains all its limit points. See what I said for limit point. What I said for closed set. If at all a limit point of A, that must be a member of E. If nothing limit points are there, means what? Automatically it's closed set. Understand? Nothing limit points are there for the set means the set must be a closed set. If there is a limit point, that must be a member of E. If nothing limit, E prime is empty. Therefore, no need to check it, right? It is redundant. Always closed set. So what you observe? This is true for any metric R, not only R. That means what? What is the notice? Every subset of discrete metric space. We have seen just now open set, not only open, it is closed. That means any subset of a discrete metric space is closed open set, means both open as well as a closed set. So any subset of discrete metric space, both open as well as closed set. Right? And properties. So first one is closed set. This is the characterizations of closed set. Is closed set if and only if there is another version E complement is open. E's complement is open set. Right? E is closed set means if and only if E complement is open set. So this is a very, very important argument. E is closed set if and only if E complement must be open set. Second is any open set. In fact, you need to write this. Every neighborhood is also open set. Every neighborhood is an open set. You take any neighborhood in a metric space, that must be open set. Right? So this is statement. Why? Because you give me any metric space. Suppose this is my neighborhood. See, neighborhoods may not be symmetric. It can be anything. It can be any shape according to the metric and space. So you suppose you take this point. I can adjust some neighborhood which is inside the set. If you give me this point, I can adjust some neighborhood which is inside the set. Therefore, every point is interior. Therefore, every neighborhood is an open set. Every neighborhood is an open set. Right? Every neighborhood is open set. Is it closed? No, it may not be. May not be closed. You have seen R with respect to usual. This neighborhood around 0 with the center 1 is nothing but what? 1 minus 0, 1 plus 0 minus 1. 0 minus 1, 0 plus 1. It's nothing but what? Minus 1, 1. You know, minus 1 is a limit point, but minus 1 is not a member of E. Minus 1 is a limit point of E, but minus 1 is not a member of E. Therefore, E does not contain all its limit points. That means neighborhood does not contain all its limit points. Hence, it's not closed. Right? Next. Arbitrary intersection of open sets. Open sets is also open, not intersection, union. Arbitrary union of open sets. Open sets is also open. Means you give me any, you take any arbitrary collection. Any class, you take any class of open sets in a metric space. This union must be open. The same metric space X. Right, this is a property. Right. Next, finite intersection. Open sets is also open. That means you give me any collection G1, G2 is any finite collection of open sets. How many members? N members. That implies you take an intersection, finite intersection is also open. This is standard theorems in Rudin. The same proof which you work for real analysis also. And it cannot be, it need not be true for infinite collection. We have seen example in basic analysis course, of course. It cannot be extended to infinite collection. Right? Why? Because each 1 by n to 1 by n open in segment. According to Rudin language, this interval is nothing but segment. This is Rudin language, not Siemens. According to Rudin language, this type of intervals, open interval a comma b, is nothing but segment. Minus 1 by n to plus 1 by n. So therefore, this every point is interior point. Yes or no? Give me any point, I can adjust some neighborhood which is inside the set. Give me point, I can adjust some neighborhood which is inside the set. Give me up any point, I can adjust some neighborhood which is inside the set. Therefore, every point is interior point, hence it is open. Right? But if you take the intersection, what do you get? 0, right? What is the common point? By Archimedean property, it is 0. This is 1. Suppose you take this is 1. What is my first set? Minus 1 by 1, 1 by 1. Means minus 1, 1. What is my second set? Minus 1 by 2, plus 1 by 2. Next, minus 1 by 3, plus 1 by 3. So they are nested to 0. They are nested to 0. They are closer to 0. They are squeezed to 0. Therefore, This is nothing but what? Zero set. Right? So, 0 is not open. Why? Because 0 is not interior point. Right? This 0 is not interior point of 0. Why? Because I never adjust a neighborhood which is inside the set. Right? This is not an interior point. 0 is not interior point. Therefore, it's not open. Therefore, arbitrary intersection of open sets may not be open. Next, fifth one. Arbitrary intersection of closed sets is closed. You take any arbitrary collection of closed sets, any class of closed sets, any class that you started with closed sets. It can be countable, it can be uncountable. Any class of closed sets in metric space. This arbitrary intersection is always closed. Right? Next. Finite union of closed set is always closed. Right? Give me any finite union, finite class of closed sets. But finite class of closed sets. But the thing is, that means this union, if you take Fi is always closed set. All right. What about arbitrary union? Arbitrary union of closed sets may not be closed sets. We have seen in the basic analysis course, which works because it's a metric space. Right? Each singleton is always closed set. You need to write a property, in fact. This is 1, 1. So one property is every finite set is closed set in metric space. Every finite set is always closed set. This is Rudin corollary. Why? Because a finite set has no. Confuse. In the rastam. So therefore, we have seen this. Go through this. It has no limit point because the finite set. Therefore, it's always a closed set. Each singleton is always closed set. Right? But I'm working with rational singletons. Not only rational, irrational is also closed set because singleton set has no limit points. Therefore, you take the union. You take the union of this. What do you get? Rationals. Total collection of all singletons over Q is nothing but what? Rationals. It is not closed. Why? Root 2 is a limit point. So no, root 2 is a limit point because you give me any neighborhood, root 2 minus r, root 2 plus r. It contains at least one rational number by density property of rationals. So therefore, any neighborhood that you take any small neighborhood contains at least one rational. Therefore, root 2 is a limit point of Q, but root 2 does not belong to Q. Therefore, it's not closed. So arbitrary union of closed sets may not be closed sets. Right? Seventh property. Every finite set. Write this argument. If P is a limit point of the set E, if and only every neighborhood of P. Actually, what is my definition of limit point? It contains at least one point in the set E other than P itself. But in metric space, every neighborhood of P contains infinitely many points, in fact, because every metric space is R stuff. So it contains infinitely many points in the city. This may not be true in topological space, any arbitrary topological space, but the thing is, we are working with metric space. So every neighborhood of P contains infinitely many points of the set T. That means every neighborhood of P intersects the set T at infinitely many points of the set T. Right? You take any example, and in fact, you take any example for understanding purpose. Give me suppose 0, 1, open 0, 1. Right? So 0 is a limit point. You give me any small neighborhood, it contains at infinitely many points. These are infinitely many points, pink region. Therefore, give me any neighborhood of 0, it contains infinitely many points of the set T. Therefore, in order to say that a P is a limit point of the set T, found only, you take any neighborhood of P, that should intersect the set T at infinitely many points. But this won't happen in topology. One way is okay, but converse may not be true. Eighth one. So by this seventh argument, we can easily derive that every finite set has no limit points. Why? Because what I said, in order to say that as a point is a limit point of the set E, that must every neighborhood of P, that it should intersect the set E at infinitely many points. But you are taking an infinite set. How can you intersect the set E at infinitely many points? No, right? You've taken a set with a finite set. In order to say that if pick any point in a finite set, that every neighborhood that is started with, that should intersect the set E at infinitely many points. But it is not possible. Why? Because you started with a set with a finite set. Right? So therefore, a finite set has no limit points in a metric space. In fact, this result also cannot be true in topological space. Right? Cannot be true in topological space. This result is only true for metric space. Ninth one. Every finite set is always closed set. Why? Because it has no limit points now. It has no limit points. E price is empty. Empty set is subset of itself. So finite set has no limit points. Therefore, it's subset of itself. Right? So this is about properties about, closed set and open sets. Next definition. Perfect set. Right? You take any metric space. You take any subset of X is perfect if and only E prime is equals to E. That means every point of E is a limit point of E. Every limit point of E is a point of E. What is E prime? Derived set of E. This is a notation, right? Rudin. Right? If at all E prime is equals to E, 100%, E is a perfect set. Right? Example. Suppose you take this. Is it a limit point? Yes. Is it a limit point? Yes. Because any neighborhood that you started with contains infinitely many points. So is it a limit point? Yes. You take any neighborhood, it contains infinitely many points of the city. Is it a limit point? No. So what are the limit points? Close 0, close 1. This is exactly, therefore E prime is equals to E. Therefore it is perfect. Second one, suppose you take the same, you take a subset this in a same metric space. Is it perfect? No, right? right? 0 is a limit point, this is a limit point, this is a limit point, this is a limit point, 1 is a limit point. So what are the limit points? Close 0, 1, but it cannot be in E, right? Because 0 is not there in E. Therefore, E prime cannot be E. Therefore, it's not perfect, right? So this is about perfect set. In second example, suppose you take R with respect to discrete. You take any subset. This is subset of R. What is E prime? We have seen a discrete metric space has no limit points. It's an empty. It cannot be E, therefore it's not perfect. Right? So this is perfect. Okay. Next is closure of the set. Closure of the set means you take any subset of a metric space. You take any E is a subset of X. So closure of the set E, which is denoted by this, like this. We can call this as closure of E, which is defined by A in N its derived set. A in N its derived set. Right? This is also very, very important example, important definition. E in N its derived set. Example, suppose you take R with respect to usual, right? Suppose you take set of wall 1, 1 by 2 like this. What is closure? Closure is nothing but E in N its derived set. First, find the derived set. This is 1, this is 1 by 2, this is 1 by 3, this is 0. Is 1 is a limit point? No, because I never find it. Means you take any neighborhood that never contain infinitely many points of the set other than the point itself. So therefore, it cannot be limit point. See, చెప్పాను limit point అంటే infinitely many points of the set కూడా రైటే, because we are working with metric space. Right? Is it a limit point? No. Because I can adjust a neighborhood which never intersect the set other than the point itself. Is it a limit point? No. Is it a limit point? No. Is it a limit point? No. But is 0? 0 is yes by Archimedean property. 0 is a limit point. You give me any neighborhood of 0, minus epsilon plus epsilon, 0 minus epsilon, 0 plus epsilon. Right? You take any neighborhood, 100% by Archimedean property, you can find a stage in such a way that 1 by h is less than epsilon. But 1 by h is positive. Yes or no? But minus epsilon is less than 0. Therefore, this 1 by h is a point of the neighborhood. This 0 minus epsilon, 0 plus epsilon. No? Therefore, neighborhood of 0 other than 0. 0 less than 1 by h. No? Therefore, 0 not equals to h. Right? It's a point of E also. Therefore, it contains at least one point of the set E. You take any neighborhood, but epsilon is arbitrary. Therefore, 0 is a limit point. So 0 is the only limit point, because this cannot, the points which are left side to 0 cannot be limit point. Therefore, what are the, E is as it is 1 by n like this. What is E prime? Singleton 0. Therefore, what is my, this as it is, keep it as it is. So this is my closure. Closure is nothing but what? 1 by n union 0. This is my first one. Suppose you take this. Set of all rational number which lies between 0 to 1. What is closure? Set of all rational number lying between 0 to 1. What is closure? You need to find first limit points. Is it a limit point? Yes. You give me any neighborhood, it contains infinitely many rationals. It's a limit point. Is it a limit point? Yes. Give me any neighborhood, contains infinitely many rationals. Therefore, it's also a limit point. It's also a limit point. One also a limit point. Yes. Give me any neighborhood, contains infinitely many rationals of the city. 0 is the limit point. Yes. So what are the limit points? Close 0, 1. Right? Actually, what is E? It's nothing but Q intersection with open 0, 1. There, what is E closure? Q intersection with open 0, 1 union close 0, 1. So what is union? Close 0, 1. Right? So this is about closure of the set. This is about closure of the set. Next is dense of the set. What is dense? You take any metric space, take any subset of X, then E is said to be dense if and only if the closure is full X. That is, see, actually you know that. So before that, you need to write properties. Sorry for the inconvenience. You need to write the properties of closure. They are important. So properties of closure. So closure of the set is always closed set. Closure of the set is the smallest closed set. Closed set. In fact, superset of it. In fact, superset of it. Closure of the set is the smallest closed superset of it. Right? You take any closure which is a closed set, not only closed set. Suppose E closure is a closed set which is containing E. Suppose F also closed set which is containing E. Suppose G also closed set which is containing E. Suppose you take their closed sets. So by the theorem tells you that E closure is smallest. Understand? This is my smallest argument, right? It's a smallest closure superset of E. It's a closed set, not only closed set, it is a smallest closure set which is containing E. Right? Next argument, this is a characterization equivalent notion of closed set. E is closed if and only if E closure is equals to E. This is very important argument. You can use as a definition also. Closed set. What you have seen closed set definitions, E contains all its limit points. One of the characterization is E complement is open. We have seen properties. E is closed if and only if E complement is open. Another characterization is E is closed if and only if E closure is equals to E. Right? E closure is equals to E. Right? Third one. Suppose E is a subset of R. E is bounded above. In fact, if the supremum of E, suppose you take some X, it's a real number. So that implies this X is a member of E closure. This is also very important property in Rudin. If at all there is a supremum, that supremum is a point of the closure. If at all there is an infimum, that infimum also belongs to the closure of the set. This is also very important. In particular, if at all it is closed set, if it's closed set, so that X comma Y should be in E. Because why? E closed అయితే ఏమైందండి? E closure is equals to E కదా. So therefore X comma Y belongs to in E అన్నమాట. Using this property. E is closed in అనుకోండి, X comma Y, they are in E. Okay. So this is also very important properties in Rudin. Okay. Properties of closed sets. Next is in Japan. Yeah, dense Japan. Next is dense. Dense set. X is a metric space. E subset of X. E is dense in X if and only E closure is equals to X. So that is, E closure is equals to X means actually E closure is always subset of X because E closure is the smallest closure superset of E. It's enough to show that X is a subset of E closure. That means what? You need to show this, that is if and only X belongs to E closure for every X belongs to X. X belongs to E closure means what? Take any neighborhood. You need to mention another property also. E closure is nothing but set of all points in a metric space such that every neighborhood of X intersects E. Understand? If P is a point of E closure, if and only if every neighborhood of P intersects E. Take any neighborhood of P which should intersect C. E closure lo undalante, this is my metric space. This is my subset of E. E closure lo undalante, you take any neighborhood. Just intersect E అయితే చాలు. అదే లిమిట్ పాయింట్ అయితే intersects E other than the point itself. బట్ క్లోజర్ లో ఉండాలంటే జస్ట్ సెట్ ని ఇంటర్సెక్ట్ చేస్తే చాలు. అది ఈ పాయింట్ ఈ దగ్గర వేరే పాయింట్ దగ్గర మనకు సంబంధం లేదు. క్లోజర్ లో ఉండాలంటే ఈ ఇంటర్సెక్ట్ చేస్తే చాలు. లిమిట్ పాయింట్ కావాలంటే ఈ పాయింట్ కాకుండా వేరే పాయింట్ దగ్గర ఇంటర్సెక్ట్ చేయాలి. రైట్? సో ఇక్కడ మీరు అబ్జర్వ్ చేస్తే X belongs to E closure means what? Every neighborhood of P intersects E other than no, not other than every neighborhood of P intersects E. If this happens, E is dense in X. It's another definition. Generally, the functions use just the definition. So every neighborhood of P intersects E for every point, for every center, for every P. For every P. And this is what actually dense set. Suppose you take this example. Suppose you take any set you started with. What is E closure? E closure is nothing but E union its derived set. What is E? Open 0, 1. What is E prime? Empty. Because we are working with discrete metric space. So this is open 0, 1. It cannot be full space R. Full space R. Therefore, E cannot be dense in R. Suppose E is equals to close 0, 1. What is E closure? E closure is nothing but E union its derived set. What is derived set? Empty. Therefore, this is nothing but close 0, 1. This is nothing but is not equals to R. Therefore, this is also not dense. So can you give me dense? Only R itself is dense. Understand? If you take R, what is E closure? E union its derived set. This is R. So what you observe? Notice is only dense subset of discrete metric space. It is full space X. Right? Any dense, only dense subset of discrete metric space X is X itself. Very point dense undadu. Right? Very set undadu dense set. Suppose I take this. Right? So what are dense? Suppose you take E is equals to rationals. What is E closure? We have seen E union its derived set. What are the derived set? Real numbers. Every real number is a limit point. You take any real number, you take any neighborhood, it contains at least one rational. So every real number is a limit point. You give me P, you take any neighborhood, it contains at least one real number other than P. Therefore, every real number is a limit point of Q. Therefore, what is union? R. Therefore, rationals is dense in Q is dense in R. Right? This is about dense. Right? With this, I conclude the lecture. So, any doubts? Yeah. Please ask your doubts. Anyone? Unmute and ask. Anyone? Yes, sir. Thank you, sir. Okay, sir. Right, sir. Mamata madam.
Sir.
Okay, you have any doubts?
No, sir.
No, sir. Okay, clear. Right, sir. Thank you, sir. Okay, sir. Right. ఎగ్జామ్ ఒకటి ప్లేన్ జామెట్రీ మీద కూడా ఒకటి కంప్లీట్ ఓన్లీ నేను మనకి జామెట్రీ మీద కూడా పెడదాం అనుకుంటున్నాను, సాలిడ్ జామెట్రీ. అది కూడా ప్రిపేర్ రెడీగా ఉందండి. ఒకటి సాలిడ్ జామెట్రీ, ఓన్లీ సాలిడ్ జామెట్రీ మీద ఒకటి, రిమైనింగ్ గ్రాండ్ టెస్ట్ కూడా పెడతాను. మీరైతే రెడీగా ఉండండి, ఎగ్జామ్స్ ఎప్పుడు పెట్టినా రాయడానికి రెడీగా ఉండండి. ఓకే సార్.